We're welcoming Dr. Zhong Li from the machine learning group at Microsoft Research Asia. So he got his bachelor degree from the mathematics program in Jilin University and PhD from Peking University. His research interest is around the mathematical theory, principles, and algorithms of deep learning, and more recently, generative AI and data efficient machine learning. And he's published in top machine learning conferences and journals. And today his talk is going to be on the last topic, which is generative AI, right? So on the generalization properties of diffusion models. So Zhong, please begin.
Okay, thanks for your invitation, Professor. Hello, everyone. Today I'm going to talk about one of our recent work, which is published on Neurips 2023. It's called On the Generalization Properties of Diffusion Models. This is a joint work together with Poheng Li, now a PhD student at Stanford, Huishui Zhang, now an assistant professor at Peking University, and Jiang Bei at Microsoft Research Asia. Okay, I will enroll this work mainly from three aspects. First, I will review some background of diffusion models, talking about its success in reality. Second, I will introduce the formulation of diffusion models, including its paradigm and detailed architectures. This part is about the working regime. Most importantly, our core results and key observations will be divided into two categories. In the third part, we'll characterize the generalization properties of diffusion models from both data-independent and data-dependent perspectives. Okay, diffusion models, which belongs to an emerging family of deep generative models, have experienced a surge in popularity since they have unparalleled performance in many applications, which leads to notable commercial products and also successes, such as Dahlia, Imagine, Stable Diffusion, and Midjourney. Here are some examples to show the most typical usage of diffusion models when it is applied to text-to-image generation. Okay, besides, the diffusion model has a wide range of applications. It can be used not only in computer vision tasks, but also in areas such as natural language processing, time series analysis, multimodal learning, and scientific modeling. You can check this review paper for more details. Okay, we quickly review the background of diffusion models. Now, as a kind of a generative model, the diffusion model is under the supervised machine learning regime. For this setting, we must handle an input dataset dx with a sample size n and input dimension d. Typically, the data points are ID sampled from underlying ground truth or target distribution p star. The goal is to either explicitly model the density function p star using information from the dataset dx or implicitly synthesize new samples x new obeying the same law of target distribution without directly modeling p star. Okay, when categorizing neural network models according to their landed mathematical objects, the diffusion model is used to learn probability distributions, similarly to GAN, VE, and normalized flow. While feedforward neural networks, or MLP, or ResNet or CN are used to learn functions. And the recurrent neural networks, such as its variants, LSTM and GRU, and temporal CNNs, such as its typical examples, ViVNet and encoder-decoder architectures, including transformers, are used to learn diffusion equations or dynamical systems. Okay, Roughly, the modern method of diffusion models is to establish transport mappings that can be stochastic or deterministic between the target distribution, which is empirically observed yet unknown, and a known prior, and learn it. So here is an illustration of the working process of diffusion models. Hello, is anyone has problems? Okay, I'll continue. The leftmost is an image, we denote it as x0, sampled from the underlying target distribution P star, or denoted as P0. The rightmost is nearly a white noise, x big T, approximately obeying the Gaussian prior pi. Okay, the transport mapping is an invertible SDE system. From left to right, this is called the forward process, involving a standard SDE with a drift coefficient F and a diffusion coefficient G. From right to left, this is called the backward process, which is a reverse SDE, but it involves the target score function, that is, the gradient of log of marginal density. It's proved that the forward and backward process share the same marginal distribution at each time step. So the reverse SD can successfully generate samples when the time step back to 0, which obeys the same underlying ground truth distribution. However, we cannot directly compute the marginal density PT, since the multi-dimensional integral is not trackable to compute. So we need to learn the target score function with some neural network models. In the theoretical part of this work, we model the target score function gradient of log marginal density with this random feature model, ST theta. The random feature model is a one hidden layer feed-forward neural network with inner weights WU as its inner weights randomly initialized but frozen, not changed. Here ET is a fixed function which acts as the time embedding, and M is the width of the network, and M can be viewed as the model capacity. So we train this score network ST theta by the gradient flow, which is a continuous time idealization of gradient descent. Here I need to clarify that small t, that's in 0 to big T, is the SD time, and tau denotes the training time. Okay, the gradient flow is with respect to the loss objectives. The loss is defined as the so-called time-dependent score matching loss. The time-dependent score matching loss is a weighted average of the L2 distance between score network models and target score functions. And the weight function is lambda. Yeah, since we cannot explicitly compute the target score function gradient log PT, an equivalent objective called denosing score matching loss is more practical in applications. Here, we only introduce the conditional distributions, gradient log PT given x0. This density, this conditional density and the induced score functions are more trackable and can be computed in a closed form. So this loss can be evaluated. These two loss objectives are equivalent up to a constant. Up to a constant. This constant is not related to training parameters. Okay. Another point is regarding the choice of SD coefficients f and g. Typical examples include variance excluding SD or VG SD and variance preserving SD or VP SD. When discretizing the SD, uh, their discretizations lead to SMLD, which is a shorthand of denoising score matching with non-given dynamics, and DDPM, denoising diffusion probabilistic models. Yeah, you can choose different choices. You can choose different F and G to drive different formulations of diffusion models. Okay, this is the formulation part. Now, based on this, we can define our problem in this work. The fundamental generalization properties of diffusion models is to study the dynamics of KL divergence. This KL divergence between the target distribution P0 and the landed distribution P0 theta hat n tau. Here, the theta hat n tau is a gradient flow solution at the training time tau.
Zhong,
Yeah,
can I ask you a
yeah,
question about the
please.
previous
Yeah,
slide?
yeah, go ahead.
So I have two questions concerning the two equations, the two SDEs that you wrote in the previous slide. The first one is, do we have a result that says that any distribution can, at time capital T, if we flow it along an SDE would be a Gaussian. So that means that whatever you start with at x0, I can always flow along a stochastic differential equation at the end. I end up with a Gaussian. So that's the first question. And the second question is about the equation in the second line. Are you thinking about that as a simple SDE, or are you thinking about it as a backward stochastic differential equation where you have to end up at x capital T? Or is it like you start actually from x capital T and then you go and then at time t, which now is 0, you will find x0?
Yeah, for your first question, I think the stationary distribution, whether the stationary distribution is Gaussian or not, depends on your choice of f and g. Certainly, yeah. For this two kind of choices listed here, SMLD and DDPM, it can be guaranteed that the stationary distribution is a Gaussian.
Okay.
Yeah. For your second question. Uh, for your second question,
It's whether
So
the,
is it a
the SD is backwards.
backwards. It's
is it,
the backward SD it is not a normal SD, I think, because it involves the marginal distribution of the SD solution. So
I just mean
um,
like how do you think about solving it? Are you solving it from saying initial condition is x capital T, or are you saying that the terminal condition is x capital
X
T?
capital T, X capital T.
So is it initial or terminal
Yeah, it's the
condition?
initial of the backward process.
Okay, thank you.
Okay.
I also have a question, if I
Mhm.
may.
Yeah.
So just about the notation, so sigma in your slide, it's like the Gaussian distribution. Is that right?
Sigma.
Like on your picture, right? Yeah, if you go to the equation, yeah, here sigma in the definition of st of theta.
No, I forgot to say that. Sigma is the activation function.
It's what?
Is the activation function. Here we choose the ReLU function.
Okay, and a is
Yeah.
what? It's like it's
A
difficult.
is is ST theta is in fact a one-hit layer fit for the neural network. A is its outreach, and A is the only trainable parameter. So it's basically a linear model.
Okay, I see.
Yeah.
And can you give some insight of about what lambda means, like the weighting function? So is it?
Yeah. In the original papers of diffusion models, lambda is also selected as inversely proportional to the norm of the score function.
Okay, I see.
I guess.
Okay.
Yeah. Yeah.
Yes.
Okay. Okay. Let me continue. Okay. The problem of this work is to study the dynamics of this KL dependence between the target distribution P0 and the landed distribution P0 theta hat n tau. Yeah, here the theta hat n tau is a gradient flow solution at the training time tau with respect to uh, the empirical average of the score matching loss estimated by n training samples. So it's basically this is both of the two score matching loss is are population losses, and here we use the empirical losses, which is typically the case in practice. Okay, our theoretical results in the following are about the upper bounds on this KL dependence, on this KL metric, and this quantity can be also numerically verified. Okay. Now we first state the first theoretical results, which is the data-independent generalization gap. Here we assume the target distribution P0 is smooth. This is common since we must differentiate P0 to get the score functions. Most importantly, the key assumption is the target distribution has a compact support or finitely supported, and the others are regularity conditions. Sorry. And the others are regularity conditions. The conclusion is that under regularity conditions with high probabilities, we have this upper bound on the dynamics of KL difference between the target distribution and the landed distribution for any training time tau no less than 1. Here we have some dependencies involving almost linear input dimensions and regularities and the SD time horizon, capital T. Okay, we'll discuss in details about this upper bound in the next page. Okay. We divide this upper bound into 3 parts, I1, I2, I3. Here, I1 is the main arrow. It implies an early stopping generation gap, because if we take the training time tau with this polynomially large quantity and the model capacity M with the same order as the training sample size N, we'll drive that this KL divergence is upper bounded by a polynomially small arrow. This polynomially small is in terms of both the sample size N and the model capacity M. So this is our first part arrow, and the second part, I2, is about the approximation arrow, since you can see there is the loss at the optimal parameter here, plus 1 over m term. This term is M dependent or model capacity dependent. This arrow goes to this arrow will go to infinitely small when M goes to infinity, because this is also a classical result. Since random feature models are random feature models are universal approximators to Lipschitz continuous functions on compact domains. You can check this paper for details. Okay, the third part, I3, is in fact exponentially small in the capital T. This is also a classic result, since the stationary distribution, which is Gaussian, is in fact a log subleaf. So the convergence of the forward SD to its stationary distribution is exponentially fast. Okay, anyone has problems?
Maybe a quick question here.
Okay.
If you assume that M and N are the same order, then wouldn't the last two terms of the first L1 estimate be of different order?
For the two terms,
So if you assume M and N are the same order, right?
yeah.
In L1, then the right-hand side of the inequality, these two are different orders.
Uh,
Your
yeah.
KL is bound.
Yeah.
So
So here we just want to emphasize, we just want to state this argument can be polynomials small, but the specific order we don't care so much.
but presumably there's a minimizer of this when you vary tau.
Yeah, yes.
Okay.
In fact, we let me recall. Yeah, we basically do it in a simple way. We just let um, the first term in I1, I think, equals to 1 over tau, and drives this tau, and ignores the second term in I1.
Yeah. Okay. I see.
Yeah. So here is the numerical verification. We illustrate the dynamics of the above KL difference, and both the SE and the Adam training dynamics for multiple runs. Here, this figure is tested for Adam, I think. Okay, it's shown that as the training process, the KL difference first decreases to a low level, then rises a little bit. This verifies to some extent the existence of early stopping generalization of diffusion models. Okay. Now I state the second data-dependent generalization gap. Compared to the first data-independent case, here in this theorem, all the conditions remain the same, except that the target distribution no longer has a compact support. Here for simplicity, we only select the one-dimensional two-mode Gaussian mixture as an example. The key is to set the modes distances. The distance between the two modes are sufficiently large. This time, we can drive this upper bound, and this upper bound is polynomially large. We call this phenomenon as the mode shift effect. That is, increasing distances between modes of target distributions leads to worse generation gaps of diffusion models. Okay, here mu represents the distances between the modes. So this theorem holds in the sense that mu goes to infinity. Okay, admittedly, it's insufficient to support negative. This is a negative characterization. So it's insufficient to support the negative characterization through upbound. So in the following pages, we mainly demonstrate this adverse modes shift effect through numerical experiments. Yeah. This is a comparison of the lended densities by diffusion models applied to Gaussian mixtures with varied distances between modes and the SGD training dynamics. Here the lended densities are orange, and the target Gaussian mixtures are blue. Okay, the above rule is for near modes. You can see the mode distance is 6 mu. Since it's symmetry, the mu equals to 3. And the bottom rule is for far modes. The mode distance is 30. We can see that diffusion models can learn Gaussian mixtures with nearer modes, at least in the middle training stage. In the above rule, it's at the thousandth epoch. While for the bottom rule, faster modes, only the mode's position is limited, but the densities is no longer limited. Okay. The same phenomenon is also observed not only for SGD, but also for the atom training dynamics. Okay, we can similarly see that diffusion models can learn Gaussian mixtures with nearer modes in the middle training stage, while this is not the case for faster modes. Okay. Yeah. The numerical experiments shown above is all about some toy examples. Now we further verify these findings under the real-world setting. Here we test on the MNIST dataset using the standard UNet architecture, which is a typically architecture used in practical diffusion models as a score network. Yeah. To construct data distributions with varied mode distances, we first perform k-means clustering on the MNIST dataset. Then we select clusters with the farthest centers to form a new subset called defarthest. Similarly, we select clusters with the nearest cluster with the nearest centers to form a new subset called the nearest. And finally, we randomly selecting the same number of data samples in both new formed sub-data sets, and using the same configurations to train two separate diffusion models on the farthest and the nearest respectively, and also perform respective inference or sampling. Yeah, the training loss curves are shown in figure A, and the sampling results are shown in figure B and figure C, respectively. We can observe a significant performance gap between the trained two diffusion models. You can see that the diffusion models trained on the farthest appears a higher training loss, this orange curve, and worse sampling quality, figure B, compared to those of the nearest, the blue curve training loss and figure C. Yeah, it is, which suggests that the adverse effect of mode shift on the generation performance of diffusion models. And this adverse effect also holds and appears in general cases. Okay. Is there anyone has questions?
Is there a way to measure? So you can't compute the KL divergence in this case, right? Is there a way?
Yes, yes.
So other than visual, like do you have other measure to show that the performance varies with the
Yeah, yeah. There are several measures in traditional CV tasks, I think. There are such as FID and negative log likelihood.
and in this case, do you observe that it's I guess you only have two data points now, right? So you only have one close and one far, right? You don't have anything
Yeah, yeah,
okay.
yes, yes. Yeah, yeah. We also test not that far data subsets. But we just not plot the whole trend.
Okay.
Yeah, because the issue lies in the k-means clustering not performs very perfect in this in this task, because in the first k-means clustering, um, we should choose an appreciated key to achieve um, certain kinds of perfect clustering. So if the dataset is not clustered um, very perfect, this dataset this formed dataset will be adversely affected, I think. So this Morse shift effect is more significant on the farthest and the nearest centers and induced clusters. Okay. Anyone has questions?
Yeah, I think you can continue. We have a little question time at the end.
Okay. Okay. Yeah. To conclude, we only provide two main takeaways. Yeah. Under the data independent regime, this is for targeted distributions with finite supports. Diffusion models have polynomially small generation errors in the sample size and the model capacity with early stopping. And under the data dependent regime, this is for the target distribution with increasing Morse distances. The generalization performance of diffusion models will become significantly worse as the Morse increases. Okay, this is the paper for your references. Thank you.
Okay, thank you.